And today there is a very, very important topic to be covered, and that is called estimation and testing of hypothesis. And before coming to estimation and testing of hypothesis, there are certain important things to understand. For example, there is a terminology behind estimation and testing. For example, if there are word estimation and testing, then what do you mean by estimation? What do you mean by testing? How to frame hypothesis, maybe null or alternative hypothesis, and what is type 1 error, what is type 2 error, then level of significance, critical region, p-value. So all these things, once these things are clear, then and only then we can move on to the hypothesis testing problems. And as per my knowledge, we have to cover only the parametric test. Parametric test, that means those tests, they satisfy certain set of assumptions like normality, independence, etc. Then we go for the parametric test. And the other part, which is generally called non-parametric test, that will be covered by somebody else. Okay, so I will share the presentation and then we'll start. And if you have any question, any query, you can interrupt me anytime. If anything is not clear or you want to repeat the things, please don't hesitate. I can repeat everything. So let me share the screen. Hopefully you can see my desktop. Is the desktop visible? Anybody, please?
Yes, sir.
Yeah. Okay. All right. So again, as I mentioned, I'll start with estimation and testing of hypothesis today. This part we have already covered. Okay. So I'll give you the practical demo, maybe after 1 hour when all the theoretical part will be over. And theoretical part is the most important to understand, particularly in estimation and testing of hypothesis. So basically there are 3 words. One is estimation, another is testing, and the third one is hypothesis. So I'll explain you meaning of all the 3. First of all, let's see what do you mean by estimation. See, there is always a population, and we cannot study the entire population. We cannot study the entire population because population is generally very large. Then what we do? We take a sample out of this population, and generally we take a random sample. What is the meaning of this word random? Random means every member of the population, here it is written, every member of the population has the same chance of being selected in the sample. That means there is no favoritism, there is no biasness. Let me give you example of a random sample. Suppose in a class there are 50 students, and somebody give me this task that you have to select only 5 students. Now it may be possible that I know the name of 5-6 students. If I go by the name selection, there may be favoritism involved, there may be biasness involved, right? There may be some kind of preference of one person over the other. So it's not a random sample then, because it is just pick and choose, because you know some people. What is a random sample? I mean, the best way to select 5 people out of 50 is that what I can do, I can write down the name of each and every one on a piece of paper, mix them thoroughly. So there will be 50 different slips with 50 different names, and mix them thoroughly and pick up any slip at random. Whosoever name appears, that person gets selected. Similarly, I can go for the second selection, third, fourth, fifth selection. That sample will be at random because there is no favoritism and there is no biasness. So we always try to take a random sample out of the population, right? Because random sample, if you take, they will give you better estimates. Of course, sometimes non-random samples are also required, but most of the time we go for the random samples. So there are two things now. One is population, which is very large. Another is sample, which is a part of the population. So there will be values which are concerned with the population, and there will be values which are concerned with the sample. Now, if your values are concerned with the population, listen to me carefully, please. If your values are concerned with the population, then they are known as parameters. For example, population mean, the standard notation in statistics is mu. This symbol is called mu, mu. Similarly, population variance, the standard notation is sigma square. Population proportion. Population proportion means in the entire population, let's say I'm looking at the proportion of males or proportion of females or proportion of people, those who are suffering from some disease, or proportion of people who are having rural background, something like that. It could be any proportion. That is denoted by capital P. So if capital P is, let's say, value is 0.43, that means 43% of the people, they belong to this particular category. So this is what it means. So if your values are concerned with the population, they are known as parameters. And these parameters are generally unknown. Why? Because I cannot study the entire population. So if I cannot study the entire population, I cannot throw any light on the population mean, population variance, population proportion, because I have not gone through all the subjects in the population. That's why we always take a sample. Let's say there is a population of 50,000 people, and I take a sample of only 500, right? Now, if I take a sample of 500, then X1, X2, X500, all the observations will be available to me of 500 people. Let's say it may be related to height, it may be related to weight, it may be related to BMI or age and blood pressure, whatever. Whatever the parameters you want to study, you can study that. But all the 500 observations for the sample will be available. So if the observations are available, obviously you can compute mean. And that mean is basically called sample mean, because it is coming out of the sample. So sample mean is denoted by X bar. Similarly, sample variance is denoted by S square. Sample proportion, because in 500 people, I can always count how many males, how many females are there. So you can get the sample proportion, which is small p, right? Now, as I mentioned, if your values are concerned with the population, they are known as parameters. But if your values are concerned with the sample, then it is called a statistic. So see the difference between parameter and statistics. If your values are concerned with the sample, it is called a statistic. If your values are concerned with the population, then they are known as parameters. For example, sample mean denoted by X bar is a statistic. S square is a statistic. Small p is a statistics. Now, let's say if you have used the appropriate sampling technique, because there are methods to take out a sample from the population, and they are known as sampling techniques, like simple random sampling with replacement, without replacement, stratified sampling, probability proportional to size sampling, cluster sampling, right? Then judgment sampling, convenience sampling. There are many different type of samplings. They are used in different situations depending upon the type of study. What I'm saying, that let's say you have used the appropriate sampling technique by consulting some statistician, right? And also you have taken the appropriate sample size, because sample size is also important to compute in most of these studies, right? And now these days, emphasis on sample size is much more. And if you are taking a project from ICM or WHO, they will always ask you that you take a statistician along with, so that you can go through all the statistical things which are required right in the beginning, like sample size, sampling techniques, design, etc. So all this you need, right? Now, what do you think? If you are taking an appropriate sample size, if you have used the appropriate sampling technique, you will expect that this sample mean will give you an estimate of this population mean mu. I mean, X bar will be an estimate of this mu. Similarly, S square will be an estimate of this population variance, which is sigma square. And this small p, which is sample proportion, will be an estimate of the population proportion. Hopefully, you will agree with me, provided you have taken a representative sample out of the population. So you are basically referring back from the random sample to the population. For what? That means we have estimated, we are trying to estimate the parameters of the population based on the sample, right? And that's why this problem is called problem of estimation, generally called statistical estimation, right? For example, this x bar is an estimate of mu, s square is an estimate of sigma square, small p is an estimate of capital P. So this is what we mean by the first word, that is called estimation. The second word is testing. Now, question is, whatever the estimates you have obtained, let's say you have not used the appropriate sampling technique, you have not taken the appropriate sample size, then these estimates may not be good estimates, they may be bad estimates. So next problem comes about testing. We need to test whether these are good estimates or these are bad estimates. That's why we require the second word, that is called testing. And to test anything, we need to drive what is called hypothesis. If I want to test, I should have some hypothesis, right? So that's why these three words are important: estimation and testing of hypothesis. So we will first frame the hypothesis and then we will go for the testing. Hopefully this diagram makes some sense to you. Is that okay? Yes, please. Anybody?
Yes.
Yeah. Okay. Very nice. Now, these are the important sampling techniques, although um, we take one semester course to teach all these sampling techniques, but I'll not go through the sampling techniques. I'll just give you briefly idea about all these sampling techniques. For example, if you look at first two samplings, a simple random sampling with replacement and without replacement, these first two samplings are generally used if population is more or less homogeneous in nature. What do you mean by homogeneous in nature? For example, if I'm teaching to, let's say, postgraduate students, then all the postgraduate students in a class, they are having the same age group, same qualification, same education, right, background. So that can be considered as a homogeneous population. But if, let's say, fifth class students are also sitting there, or 10th class students are also sitting there, then it is not a homogeneous population. So, but these type of sampling, simple random sampling with replacement, without replacement, they are generally used when the population is more or less homogeneous in nature. But sometimes the population may not be homogeneous in nature, right? It could be heterogeneous population. For that purpose, we cannot use any one of these sample random samplings. Then we go for a stratified random sampling. Let's say somebody give you this task that you have to go for the assessment of health parameters in the entire West Bengal, right? Now in West Bengal, there are certain cities like Calcutta and some other cities which are having very good health facilities. But there are certain remote districts also which are not having very good health facilities. So if you are taking a sample only from Calcutta city, so obviously you are not have any assessment about the health facilities available in the entire West Bengal. So better way, what is the better way then? Better way is that West Bengal is having many districts. Suppose West Bengal is having 50 districts, right? And I want to take a sample of, say, 1000. So I'll divide 1000 by 50. So 20. So I'll go to each and every district and take a sample of size 20 from each and every district, so that the entire coverage can be made. And moreover, these districts are not homogeneous, because there may be some remote districts, there may be districts which are very close to the city, or the maybe city itself, right? So obviously we have to give the representation for the entire West Bengal. So this is how we go for the stratified random sampling. So what is a stratified random sampling? We divide the entire population into different stratas. These stratas may be districts, right? For example, we divide the entire West Bengal population into 50 districts. Suppose, I don't know how many districts are there, but in Haryana, there are 30 districts. In Punjab, there are 21 districts. So in West Bengal also, there may be districts. And now within a particular district, the population can be assumed to be homogeneous, right? So I can take the sample from a particular district. So if you take samples from each and every district, it will represent the entire West Bengal, and you can go for the assessment of the health. So this is how we apply this stratified random sampling. Then there is a quota sampling. So these type of samplings are called random sampling. Random sampling means the items are selected at random. That means with equal probability. But sometimes, for example, there are other type of samplings which are required from time to time, but they are not random samplings. For example, if I want to buy apples, now I'll not go for a random sampling. I just use my judgment. I'll go for a pick and choose because this piece is good, this is not good, this is okay, this is not okay, right? So obviously you require other samplings also. And one of this sampling is called quota sampling. Quota sampling means your quotas are already fixed. For example, if there is some admission policy, then certain quotas are already fixed. Let's say 15% reserved for ST category, 5% for defense people, 2% for handicap people, 60% for general. So these quotas are already fixed. Once you fix something, probability component is gone. That's why we are not using the word quota random sampling. Random sampling word is gone. But you cannot take more than 50% for SC/ST. You cannot take more than 5% for defense, not more than 2% for handicap. So these quotas are already fixed, right? So that's why this is called quota sampling. So sometimes we need to look at the sample from the quota sampling. Then there is purposive sampling. Purposive sampling means you are reacting according to definite purpose. For example, if somebody give me this task that you have to show that the cost of living is very high in West Bengal. So maybe I can go to certain posh locality areas and show my results that the cost of living is very high in West Bengal because I am reacting according to my purpose. So it's all again not a random sampling. Then there is a systematic sampling. Systematic sampling is generally used whenever we want to conduct huge surveys. I want to survey 4 lakh people, 5 lakh people. And generally, you must have seen these people from NSSO, people from CSO, Labor Bureau. They conduct huge surveys of 4 to 5 lakh people. How they do it? Let's say, I'll give you a very simple example. Suppose there are 1,000 households, right? I want to select only 100 households. So what I'll do, I will compute what is called sampling interval. What I'll do, 1,000 divide by 100. I will get answer as 10. Right? I'll get answer as 10. Now, I pick up any number at random between 1 to 10. Suppose number 8 appears. And you have a list of all the 1,000 households. Then the first households that will be get selected will be at number 8. And rest of them will be automatically selected according to your sampling interval. Your sampling interval is 1,000 by 100, that is 10. Now you add 8 plus 10. So next household will be 18, next will be 28, next will be 38, next will be 48, and so on, till you get a sample of size 1,000. So this type of sampling is called systematic sampling. Systematic sampling is the only sampling where the first item is always at the random, but rest of the items you can always tell. For example, if your sampling interval is 10, your first item is 5, next will be 15, next will be 25. So rest of them will be. That's why it is not a proper random sampling. Only first component is at random, rest of them are non-random. Then there is a probability proportional to size. Sometimes we divide our population into different districts or stratas. These stratas may not be of equal size. For example, one district is having a population of, let's say, 4 lakh people. Another district is having a population of 4 lakh 50,000. So they are approximately same. In such type of situation, you can go for stratified random sampling because these are stratas are of equal size, more or less. But sometimes, let's say one district is having population of 4 lakh people, right? 4 lakh people means 400,000 people, right? And another district is having population of 8 lakh. So now in this case, I cannot take equal sample from both of them. If I'm taking 100 units from a population of 4 lakh, virtually I should take 200 units from a population of 8 lakh people. So if I divide proportionately, that kind of sampling is called probability proportional to size sampling. Then there is a cluster sampling. Sometimes there are budget constraints, there are time constraints. I cannot cover the entire, all the districts, but I can divide the district into certain, say, similar districts, which are little bit similar, or which are, so let's say I divide this entire set of districts of 50 districts into smaller districts, medium sized districts, and large districts. And then I take few selected districts from small, few selected districts from medium, small, and selected districts from large. And then go for the selection of the items. That type of sampling is called cluster sampling. Okay, so all these samplings are different, used in different situations. There are other type of samplings like judgment sampling, convenient sampling, snowball sampling. They're also used sometimes. All right. So hopefully now you have some idea that how one can take a sample from the population. Is that okay? Yes, please. Hello.
Yes, yes.
Yeah. Okay. Now, sample versus population is a very, very important concept. We try to take a sample in such a way so that it should represent the entire population. You must have seen whenever people want to buy grapes, this is what they usually do. They pick up one and they taste it. If it sounds good, they buy it, and sometimes they leave it, right? If it is taste is not good. But if you ask a person from statistics, he will go one step ahead. He will pick up one from here, another one from here, possibly one more from here. Because what we are looking for? We are looking for a representative sample. Because sometimes what happens, the good ones are always at the top and bad ones are hidden behind. And if you're taking sample only from one corner, it may not give you a very good estimate. So that's why we select a sample in such a way so that it should represent the entire population. That is the idea of showing this picture. There was another peculiar diagram of showing you, or a picture showing you sample versus population. There was a very senior doctor, and he was teaching the importance of sampling techniques to the junior doctors. That what are the important sampling techniques and why sample is important. But one of the junior doctor, he said, "Sir, why to look at the sample? Why not to go through the entire population?" And then the senior doctor was wise enough and he understood his problem, and he take this junior doctor along with him to the nearby patient. And here is a patient. Ask him that you take out the entire blood of this patient. Then the junior doctor said, "Sir, if I take entire blood of this patient, the patient will die." Then the senior doctor asked him, "Now what you will do?" He says, "I'll take a sample." So that is the idea of taking a sample. You cannot, for example, if somebody is having a, let's say, infection and goes to a doctor, doctor will not cut his stomach and see what is inside. He will ask you to go for some blood test or maybe ultrasound. And whenever we give a blood test, you are just giving a sample, not the entire blood of your body, right? Your entire body is your population, but sample of the blood, that represents the entire blood of your body. That is the idea of sample versus population. It should represent the entire population. All right. What is the representative sample then? Look at the definition. A sample that represents the characteristics of the population as closely as possible. For example, you can see there is a picture of a kangaroo, the national bird of Australia. That's a target population. And then there is a baby. Baby represents the entire characteristics of the mother. That's a representative sample, right? because it represents the entire characteristics of the mother. But suppose I replace this baby with a baby of a dog or a cat. Do you think it will be a representative sample then? It won't be a representative sample, right? Because it does it in that case, it will not represent your population closely. So that is the idea of representative sample. Hopefully, this terminology is now clear to you. What do you mean by sampling techniques? What do you mean by representative sample, right? What do you mean by sample versus population? Now I will move on to some statistical terminology like type 1, type 2 error, hypothesis framing, and all these things before going into the practical examples of the things which we want to do with the help of R. Okay, so these will be your learning objectives today: to understand the role of significance test, to distinguish between null and alternative hypothesis, critical region, level of significance, interpretation of p-value, type 1 and type 2 errors. I'll explain you each and everything, and then we'll move on. Now, people get confused between writing hypothesis. First of all, clearly go through the definition of hypothesis. A tentative statement, you see, because what is our aim? Our aim is to estimate the parameters of the population based on the sample. That is the entire crux of the statistics. We cannot study the entire population, right? So hypotheses, they are framed only for the population, not for the sample. But we want to verify based on the sample. So here is the statement: a tentative statement regarding the population, not regarding the sample. I'm writing a tentative statement regarding the population, relating to a certain phenomena. Relating to a certain phenomena, it could be height, it could be weight, it could be IQ, it could be BMI, in which the researcher is interested, in which you are interested, and wants to verify on the basis of the sample. And you have to verify whether your estimates are closer to the population parameters or not. Because as values associated with the population, they are known as parameters. Values associated with the sample is called a statistic, right? Now, a tentative statement regarding the population. For example, let's say Vishwa Bharati. Vishwa Bharati is one of the university in West Bengal. Even I got a chance to visit this university several times, but last week I also visited. I was in Calcutta, near Calcutta. I mean, I landed at Durgapur, and then close by there is a Vishwa Bharati, right, for conducting some workshop. And that's why I met the Daya Shankarji on that day in his office. All right. Let's say, suppose in West Bengal University or this Vishwa Bharati University, suppose there are 20,000 students. I don't know how many, but let's say there are 20,000 students. And I want to estimate their height, right? Now, I cannot go through all the 20,000 students. But suppose I can always take a sample of people from the entire university. If there are 50 departments, let's say I take a sample of 10 from each and every department. So 15 to 10, you are having a sample of size 500, right? And based on this, I can compute what is the mean height. And then I'll try to estimate whether this is closer to the population mean or not, which is unknown, right? So I want to make inference about the height in the population. Similarly, you want to make inference about the weight in the population or some parameter. Hopefully you understand what I'm trying to say. This is what we mean by hypothesis. Now, these hypotheses are generally of two types. So I'll take up one example. One of the hypotheses which we need to look at is called null hypothesis. We need to frame this hypothesis before we plan our study. I mean, once we plan our study according to our objectives, we need to frame null and alternative hypothesis. For example, if somebody is interested in IQ, intelligent quotient, and his claim is that the mean IQ of this population, what I'm presuming, is likely to be 100, right? That is his claim, his or her claim. So the parameter for mean in the population is mu. So I am framing the null hypothesis. Whatever is the claim, please listen to me carefully. Whatever is the claim of a person, we always put under H naught. So H naught is a null hypothesis. So claim is that the mean IQ, so he's referring to mean, parameter of mean in the population is mu. So his objective is that mu should be equal to 100. That is the presumption. You want to test this. So I will frame the hypothesis that mu is equal to 100. Now, if it is relating to, let's say, not IQ, it is relating to height, that the mean height, I'm thinking that it should be around 160 centimeter. Okay. Then hypothesis will be mu is equal to 160 centimeter. If it is relating to weight, let's say I'm thinking that weight should be around 57 kg of the girls students, let's say, then H naught will be mu is equal to 57 kg. And if it is not, if it could be related to two populations also. Let's say there is a West Bengal, there is Assam, another state. And I want to compare the mean heights, whether the mean heights of West Bengal people is more or that is Assam people is more, right? So I'll take a sample from West Bengal. I'll also take a sample from Assam. And what will be my hypothesis? First of all, I assume that both of them are equal. So if the mean population of this West Bengal height is mu1 and that of Assam is mu2, so my hypothesis will be under H naught that there is no difference between the heights of people from West Bengal and those from Assam. So hypothesis will be mu1 is equal to mu2. So this is how I'll frame the hypothesis, that there is no difference. Then I'll actually check whether my claim is true or it is false. So under H naught, whatever is the claim, you always put under H naught. Hopefully you understand how to frame this null hypothesis. It's not necessary you are always having mean. You can also test proportion. Let's say somebody has an idea that 40% of this population is likely to vote for this party, maybe BJP or Congress. So H naught will be, capital P will be equal to 0.40. 0.40 means 40%, right? Similarly, if somebody want to test about variance, that variance of this population is likely to be, say, 5. Now, I'm not talking of mean, I'm not talking of proportion, I'm talking about variance. And the symbol for variance is sigma square. So my hypothesis will change. I will write sigma square equal to 5. This is what I want to test. Yes, please. Are you clear how to frame null hypothesis? Yes, please. Anyone?
Okay, yes.
Is this clear?
Yes.
Okay. Then, to every null hypothesis, we have to frame the alternative hypothesis also. What is an alternative hypothesis? Which is complementary to the null hypothesis, And we write here H naught. Sometimes the alternative is written as H1, or some people also write HA. HA stands for alternative. So one of the alternative is mu is equal to 100. One of the alternative is that it may not be equal to 100. So I will write alternative that mu not equal to 100. Now, if I'm writing mu not equal to 100, it could be less than 100. It could be more than 100. I don't have any idea. I'm simply saying not equal to 100. It could be less, it could be more. Right? All right. Now, because I don't have any idea it is whether it is less or it is more, that's why this type of alternative is called two-sided alternative. Two-sided alternative. But sometimes people are 100% sure about something. That, let's say, these are very, very good students. And I am 100% sure that mean IQ of this population will be, mean IQ of these students will be more than 100. Person is 100% sure. If somebody is 100% sure, then the alternative will change. I'll write mu greater than 100 because person is 100% sure. Similarly, some person may be 100% sure about that these are very dull students. I know their mean IQ cannot be 100. I'm 100% sure it will be less than 100. Then again, alternative will change. You will be mu less than 100. So this greater than, this less than, both of them are one-sided. To distinguish between greater and less, we write this as one-sided right tail because it is on the right hand side, greater than. And here we write left tail because it is on the left hand side. So your alternative, depending upon your research problem, it could be either two-sided or it could be one-sided. And further, if it is one-sided, it could be right tail or it could be left tail, right? Now, many people get confused and they ask me questions, sir, where to use two-sided, where to use one-sided? Let me make it more clear. If you are sure that something is likely to happen 100%, then you use one-sided. If you are not sure what will happen in the population, then use two-sided. As simple as that. Let me give you an example of one-sided. Right? Let's say, suppose patients comes to the doctors and doctor note down their blood pressure levels. And there are 20 patients and all these 20 patients are suffering from low BP, low blood pressure. Now, doctor knows, and we also know, that there are very well-tested medicines available in the market. People are using for the last 20, 30 years. They are very well-tested. And if you give these blood pressure medicines to the patients, their blood pressure will come to normal. So doctor give them this blood pressure medicines and call these same patients after 3 months. Now, these are very well-tested medicines, results-oriented. So what the doctors will expect? That this time after 3 months, these patients who were suffering from the low BP, now at least their BP should come back to normal. Yes or no? Yes, please.
Yes, sir.
Yeah, right. So that means doctor is 100% sure there. If doctor is 100% sure, we are going to use that their blood pressure will be greater than what they were having earlier, mean. Right. So that is there we use one-sided. But if you don't have any idea, then you safe to use two-sided, because I don't know whether it could be IQ is less than 100 or greater than 100. So I'll simply say not equal to 100. Let me tell you, in 60 to 70% of the cases, we use two-sided because we don't have any idea in the population what will happen. One-sided to be used only if somebody is 100% sure. As simple as that. So hopefully how to frame null hypothesis, how to frame alternative hypothesis, these things are clear. If you still have any question, you can ask me. Is there any question about null and alternative hypothesis now? Or is it okay? Hello?
Okay, sir.
Okay, all right. Let's move on. And very important part of statistics is type 1 and type 2 errors. See what is, just look at the top of the table, second line. What is written in green line? No study is perfect. There are always chances of error. If let's say there is a basket which contains 100 apples. Do you think if I take that basket, all the apples will be okay? Maybe 2-3 pieces may be of bad quality. It is likely to happen, right? You cannot expect everything to be 100% correct. There are always chances of error. And these errors in statistics are of two types. One is called type 1 error. Another is called type 2 error. Type 1 and type 2 errors. Now you are familiar with what is H0, null hypothesis, what is alternative H1 or HA, alternative hypothesis. So read this table like this. Here is a decision. Here H0 is true, H0 is false. So read the table like this. Reject H0 when H0 is true. Something is of good quality. H0 is true means something is of good quality, but it has been rejected. That means it is an error. And this type of error is called type 1 error. Right? And this generally happens in selection procedures because there may be a very good candidate, but the other candidate may be having pull or push. And sometimes the good candidates are not selected. And those people who are having pull and push, they are being selected. That type of error is basically type 1 error. Reject H0 when H2. Something was of good quality, it has been rejected. And then the university or college have to suffer for how many years? If some not a very good faculty is being selected, university or college have to suffer for how many years? 30, 35 years, deadwood planted for 35 years, right? Because you have committed the type 1 error right in the beginning. Very serious error. What is type 2 error? Accept H naught when H naught is false. Something is of bad quality. H naught is false means something is of bad quality, and you are accepting that. That is also an error. And that type of error is called type 2 error. And every day we have this error. For example, let's say I want to buy apples and there are a bulk of apples lying over. And I can see from the face that these apples are not of good quality, right? But the owner says, sir, you have to just take 1 kg or 2 kg. You just pick and choose. I just apply, use my judgment, pick and choose, bring 1 kg home, and my entire family consumes, and we got food poisoning. Doctor charged me 10,000 rupees for my family to treat. Whose loss is this? That's my loss because I accepted a bad lot. So accept H naught when H naught is false. Something was of bad quality and you are going to accept, that is type 2 error. It's more serious, in fact, because in economics, this type 2 error is called consumer's risk, because you have to consume the items, you are accepting that. And this is called producer's risk, right? So hopefully these diagonal elements, this is type 1 and type 2 errors. What could have been the correct decision? Correct decision have been reject H naught when H naught is false. Something is of bad quality, you also rejected. That's a correct decision. Another correct decision, accept H naught when H naught is true. Something is of good quality, you also accept it. That's a correct decision. So off diagonals are correct decision and diagonals are errors, type 1 and type 2 errors. Hopefully, now these are errors, type 1 and type 2 errors. The smaller the error, better will be experiment, right? What do you think? These errors should be small or these errors should be large? Yes, please, anyone?
Small.
Small. These errors should be small, right? So how to make, that's why there is a statistical testing. We want to control these errors so that these errors are minimum, right? Okay. There are some other examples of type 1 and type 2 error. Let's look at this thing. What is type 1 error from the medical point of view? From medical point of view, type 1 error sometimes is also called a false positive. Initially, when COVID-19 appears in 2019, 2020, in the beginning of 2020, people were not aware of any kind of testing procedure. And there were very false positive cases. What is false positive? The person doesn't have a disease. The person does not have the disease, but the test says do have. Test says that the person has a disease, but actually he was not having. He was not having. Then where the person will be put into, he will be put into the hospital where there are other COVID patients. So that is the result of false positive. And initially in the many countries, the ratio was very high. This false positive rate was very high. It was about 30%. So out of the 130% were wrong tests, basically, right? So, but later on, after 3-4 months, you see all the testing procedure was in place, and then we able to this type 1 error reduces, basically. Looking at the court example, convicting an innocent person. Person doesn't have done any crime, but he has been convicted. That's a type 1 error. Look at type 2 error. Type 2 error is also called false negative, medical point of view. The person has a disease, person is having COVID-19, but the test doesn't pick it up. Test says they don't have. And if the test says they don't have, person comes back home, there are 5 members in the family, all of them will be affected. Because it's a false negative case. So you have to be very clear. That's type 2 error. Court example, not convicting the guilty. The person has done a crime, but the judge has let him go. He may kill a lot of other people. He was not found guilty. That's type 2 error. So all these type 1 and type 2 errors are very, very serious errors. And we want these errors to be small. Okay. The next thing, before I move on to now the practical examples with some parametric test, is called level of significance. You must have gone through in your research papers that we take 5% level of significance, we take 1% level of significance, and without much thinking what this level of significance is, why statistics people take 5%, why they take 1%. Let me clarify this. Let's say I give you a basket, and in basket there are 100 oranges, and 40 of them are of bad quality and 60 of them are good quality. Will you buy that lot or you will reject that lot? Yes, please. Anybody? 40 are of bad quality, 60 are of good quality. Will you buy that basket or you will just reject it? Yes, please. Anyone? Let me just repeat my questions. I am giving you a basket with 100 oranges. 40 are of bad quality, 60 are of good quality. Now, will you accept this lot or you will reject this lot? Very simple question. Yes, please. What do you think? No answer. Yes, please. 40 are bad quality, 60 are good quality. Will you accept or will you reject? Hello? Are you with me? So, I mean,
Sir,
I'm saying if you will accept,
yes, sir.
then you are straight away losing. If you are accept, will you? Okay. If there is a basket, 40, there are containing 100 oranges, 40 are very bad quality, 60 are good quality. Now, my question is, will you accept this or will you reject this? I will not
Sir,
take
reject.
this. Huh? Yes, please. Hello? Yes, please. Whatever you say, please say something.
Sir, if he
40.
allows me that, सर अगर वो मुझे अलाउ करता है कि वो 60% जो एप्पल है उसका
नहीं
पैसा
नहीं
देने
नहीं,
के
वो
लिए तो मैं ले
अलाउ
लूं.
कुछ नहीं कर रहा. See, he is charging the full. He is charging from you the full basket money. He is not
Then
allowing you to do anything. What I'm
we should
saying, will you
reject.
buy this lot or you will reject this lot? Question is simple.
Reject.
Reject simply. It's a simple thing that if there are more bad pieces, you will reject that lot. As simple as that. But there should be some limit, na? Let's say only 1 or 2 pieces are of bad quality. Only 1 or 2 pieces are of bad quality. Will you accept or will you reject now?
Accept.
We will accept. We will accept this, right? This is what I'm asking. But there should be some limit. There should be some limit. And the maximum, or listen to me carefully, please. And the maximum allowable limit in statistics, we call this as 5%. That out of even 100 oranges, if up to 5, that listen to me, if up to 5 are of bad quality, still I can accept that lot. But if it is beyond this, I will reject this lot. That's why this is called a level of significance. That means you cannot go beyond this level. You cannot go beyond this level. That's why in many of the research papers, it is we take 5% level of significance. 1% means you can accept, you can only accept if there is only one bad quality, rest of them are okay, which is generally not achieved. You have to give little bit of flexibility. That's why we generally take 5%. I'm talking of a general manufacturing process. You cannot expect everything to be 100% correct, but level of significance has to be fixed in advance before conducting the study, depending upon how sensitive is your experiment. Sometimes you can afford 5%. For example, in general manufacturing process, if out of 100 shirts I am buying, maybe 2-3 pieces are bad, I can still accept that lot. But sometimes if your experiment is about testing of aeroplanes, and I fix their 5% error. That means if 100 aeroplanes will fly, 5 of them are likely to fall. Who will sit in the aeroplane? Nobody will sit in the aeroplane, right? So there you need to fix this level to be very, very small. Maybe 1 in 1 lakh, maybe 1 in 2 lakh. There are air accidents, but they are very, very rare. So level of significance has to be fixed much advance before conducting the experiment. Okay, so hopefully the level of experiment is clear to you. Next part is, it is basically probability of type 1 error. Probability of type 1 error is called size of type 1 error, and the maximum size which can afford is called level. Basically, maximum size which can afford is called level. For example, I will say I can afford only 5%, 5% rejections. Okay, then fine. Somebody can say, okay, I'll go up to 10%. then for him the level of significance will be 10%. Doesn't matter, but not for me, right? So then there is beta. Beta is called size of type 2 error, which is probability of type 2 error is called beta. Beta as such is not important. Let me clarify. Beta as such is not important. What is important is 1 minus beta. 1 minus beta is called the power of the test. 1 minus beta is called the power of the test, right? The power of the test is directly proportional to your sample size. It is also directly proportional to your sampling techniques. For example, if you have not taken the appropriate sample size, you have not used the appropriate sampling technique, then power of your test will go down. And there are comments from the referees that you have applied t-test, you have taken a sample of size 10 only, or 9 or 10, but please provide the power of your test. And when you check the power, it was just 40%. And that doesn't make any sense then, because you have not taken the appropriate sample size. So that is what do you mean by the 1 minus beta is more important, power of the test. Then there is a p-value. Now, for every software, whenever we apply certain test, it will give you a p-value. Yesterday we have seen, even for correlation test, you have a p-value. Regression in many of the, there was star mark. They're all p-values. What are these p-values? Smaller the p-value, greater is the evidence against null hypothesis, right? Because your p-value determine basically whether you are moving into the acceptance region or you are going into the rejection region. If you have a small p-value, you are definitely going into rejection region. If you have a large p-value, which is more than 0.05, you are going into acceptance region, you to accept the hypothesis. And we compare this with alpha. Alpha is already fixed. Alpha is your level of significance. We generally take this as 5% or 1%. And software will give you p-value. What you need to check is only reject the null hypothesis if your p is less than alpha. Let's say your p-value is 0.002. Alpha is 5%, 0.05. So obviously it is less. So you will reject your null hypothesis. But suppose your p-value is 0.259. Alpha is 0.05. So 0.259 is more than 0.05. Then obviously you will not reject. You will accept the hypothesis. So I'll give you a little bit idea about p-value later on also. But for the time being, there is always inverse relationship between test statistics and p-value. If your test statistics value is very large, which whatever you are computing, whether t-test or f-test or chi-square test, if that is very large, p-value will be small. And if your test statistics value is small, p-value will become large. So there is inverse relationship. That is the concept of p-value. So this green region is your rejection region, right? And this is a p-value. P-value is nothing but area outside your computed value. Whenever there is a standard normal tables, suppose I take alpha to be 5%. For alpha to taking to be 5%, the critical value will come out to be 1.96. Since it is a two-sided alternative, suppose it is a two-sided alternative, so this alpha, which is 0.05, will be equally distributed on both sides. 2.5% on this side, which is this green region, 2.5% on this side, which is another region, because it is two-sided. I don't know whether mu is less than 100 or mu is greater than 100. So equal distribution. That's why I'm saying alpha by 2.5 on either side. Green region is your rejection region. Okay. Now you are computing the value of the test statistics. Suppose value of the test statistics, these are the critical points. At 5%, this value is 1.96. Obviously, this is symmetrical. So this value will be this line is minus 1.96. This line is 1.96. Suppose my value is coming out to be 1.25. So 1.25 lies between minus 1.96 to 1.96. And this is white region is acceptance region. So I'll accept the hypothesis, right? But if it goes to this region or it goes to this region, I will reject the hypothesis. Let's take one example. For alpha is equal to 0.05, the critical points are minus 1.96 and 1.96. Suppose if your exact value, is coming out to be 1.96, then look at the definition. P-value is nothing but area outside the computed value. So beyond the area outside 1.96, area outside minus 1.96. So this area is 2.5%. This area is 2.5%. Add the two, 5%. So your p-value will be exactly 0.05. Okay. Now, suppose your computed value is not 1.96. Your computed value is 2.79. Then obviously it will lie somewhere here, 2.79, because 1.96 is this line. 2.79 will be here.
Yes.
And then minus 2.79 will be here on the opposite direction. And what is
Yes.
p-value? P-value will be area outside 2.79. So it will become less. It will become area, green region will become less. It will become smaller. So your p-value will be certainly less than 0.05. So p-value, whenever you are increasing your test statistics value to 2.79, p-value is becoming small. Let's take another example. Suppose I take test statistics value as 1.25. So 1.25 will be somewhere here, right? And minus 1.25. So what is p-value? P-value is area outside. So area outside will increase now. Area outside will increase. And if the area outside will increase, it will cross this limit of green. It will move on to the white region. So it will be more than 0.05. So if p-value becomes more than 0.05, you are definitely accepting the hypothesis, not rejecting the hypothesis. So this definition is written in my book. P-value is nothing but area outside the computed value. Just look at the area outside. If area is very, very small, you will reject. If area becomes more, you will accept because it is moving into the white region. Okay, so that is the concept of p-value. Now, since I have to cover parametric test, so I'll go for a little bit of theory one by one. First, we will cover t-test, and after the around 4:30, maybe I'll be able to cover all the t-test. And in the second session, we will be covering one-way ANOVA, then two-way ANOVA, and also repeated ANOVA, and all these things will be in the second session. But plus try to understand, please try to understand that there are two types of tests in statistics, parametric and non-parametric test. What are parametric tests? Parametric tests are applicable to such type of data which satisfy certain set of assumptions. What are those assumptions? That your data should come from normal distribution. How to check the normality of the data? I will tell you today how to check the normality of the data, right? So observation must be independent. Observation must come from normal distribution. And the third important is hypothesis must involve population parameters. What are population parameters? Mu, sigma square, capital P. So that means your testing should be around mean, it should be around variance, or it should be around proportion. So hypothesis must involve this thing. Of course, parametric procedures may be applied only for measurement data. I mean, height, weight, blood pressure, all these are measurements. It cannot be applied to a categorical data. Yesterday, I have given you idea about categorical data. If there is a gender like 1 and 2, please do not go for parametric test. They are not applicable. Parametric tests are applicable only for measurement kind of data. And they will, answer will be given by the softwares. They are difficult to compute by hand, but answer will be given by the software, right? And remember one more thing, parametric tests are more powerful than the non-parametric test. Wherever it is possible, try to go for the parametric test, right? Unless or otherwise it is not possible, then and only then you go for the non-parametric test. How to check the normality of the data? Today we will do it. So I'll apply this. We'll plot this histogram today. And if the shape of the histogram is almost symmetrical, you will say data is coming from a normal distribution. Another is box plot. Today I will show it to you how to draw this box plot to check the normality of the data. There is a median. And if median is right there in the center, then data is coming from a normal distribution. Third type of plot is called a normal quantile plot. We will also do it today. So you can draw the quantile plot. And if your points are along a straight line, then again, it will verify that your data is coming from a normal distribution. Now, sometimes these of course, graphical procedures are much powerful to check the normality of the data. Graphical procedures are much more powerful to check the normality of the data. But sometimes, for example, this is a shape of the histogram. Now, with the help of this, how to read the histogram? First of all, you all look at the highest bar. Here is the highest bar. Then from this highest bar, you drop a line. I drop a line. And then count how many bars on the left hand side. So how many are on the left hand side? 1, 2, 3. But how many bars on the right hand side? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bars on the right hand side. Only 3 bars on the left hand side. So that means data is not symmetrical. Data is not symmetrical. So if data is not symmetrical, your curve will look like this. It will move from here, it will go up to the top, then move on the right hand side the more. This is a normal curve. So if your data would have been normal, all these bars, they should have been within the curve. But do you think all the bars are within the curve or they are outside the curve? Yes, please.
Outside.
They are outside. If they are outside, that means data is not having a normal distribution.
Symmetric.
Okay. The second plot is called box plot. Box plot is very easy to compute. Today we will do it. For example, the lower end of the box is placed against Q1 value. Q1 means yesterday I have computed Q1, that 25% of the observation will be below this point and 75% above this point. So lower end of the box is placed against Q1. The upper end of the box is placed against Q3. And there is a box between Q1 and Q3. Then this is called whisker. Whisker is from the middle of this upper portion. It will go to the highest value present in the data. And this will go, lower whisker will go to the lowest value present in the data. And this is called the median. So if median would have been right there in the center, then data would have been normal. What do you think? The median is there in the center? Yes or no? Yes, please.
No.
No.
No,
So
sir.
if it is not in the center, then the data is not following a normal distribution. So if you tilt this to 90 degree and then draw a curve will look like this. This curve, it will stretch to more to this side. So that means it is positively skewed. So graph also, if you look at this, this is positively skewed. And the third type of graph which we can draw is called QQ plot. And it's for the same data. I have drawn the box plot for the same data, histogram for the same data, QQ plot. Now this is the standard normal line. And these are the quantiles of your data. What is a quantile? Quantile is nothing but any fraction of the data. For example, if there are 30 observations, you arrange the data in order, then the first observation will be 1/30th part of the data. Hopefully you will agree with me. Second will be 2/30th part of the data, 3/30th part of the data. So these circles are quantiles of your data. And this is a standard normal line. If your data would have been coming from a normal distribution, all these circles, all these points or the dots, they should have been on this line. But there are deviations here, there are deviations here. That means data is not coming from a normal distribution. So there are 3 ways to check the normality of the data. One is histogram. Shape of the histogram should be symmetrical. Another is median line should be there in the center of the box. Third is all these quantiles, they should be on the line. If these, all the graph, they are giving you the same picture because they are for the same data, that the data is not following a normal distribution. So these are some important graphical procedures. Now, sometimes what happens, it may happen that there is a bar in the center, right? And there are 4 bars on the left hand side and 5 bars on the right hand side. Very, very close contest. 4 bars on the left hand side, 5 on the right hand side. And then you are in a fix. Should I take this normal, not to take this normal? Same way it can happen here. That your median is very, very close to center, but not exactly in the center. It is close to center. Then you are in a fix. Should I take this normal, not to take this normal? In such type of situation, listen to me carefully. In such type of situation, what we do, we go for these type of tests. And today we'll look at the normality of the data. So it will test the hypothesis H0. It will test the hypothesis H0 that data is coming from a normal distribution, or data follows normal distribution. That is your H0. Alternative, data is not coming from a normal distribution, or data doesn't follow normal distribution. So it will give you a p-value. First test is Kolmogorov-Smirnov test. It will give you a p-value. Alpha is fixed. So if your p is less than alpha, you will reject H0. That means data is not coming from a normal distribution. But if p-value becomes more than alpha, that means then you have to accept. That means yes, data is coming from a normal distribution. So it will give you a p-value. Similarly, Spiro-Wilk test will give you p-value. Similarly, Anderson-Darling test will give you p-value. But out of this, we will go for Kolmogorov-Smirnov and Spiro-Wilk test today. These two are very important tests. People sometimes use this test, but these two are more powerful, right? These two are more powerful tests. Okay. So I have given you some idea how to check the normality of the data, and in the second practical session, we will show you how to check this. Okay. Now there are two types of parametric test. There are two types of parametric test. They are used for large samples. They are also used for small samples. If you are using this for large samples, they are generally called Z statistics. And if you are using this for small samples, that is called t-test or t-testing. Right. Now, question is, in many of the softwares, including R, including SPSS and Jamovi, etc., they are just having T statistics. They are not having Z statistics. Of course, in Minitab is having Z statistics, but R, what we'll do today, and SPSS, they are using only T statistics. What is the reason? Let me tell you the reason. The reason is very simple. Because whenever your sample size is small, you are going to use t-test. But when sample size becomes more than a sufficient number, like 30, 40, 50, or 100, actually your t-test approaches to z-test. T-test becomes basically equivalent of z-test. So what does this mean? That means t-test is applicable. So whether you are taking decision based on z-test or you are taking decision based on t-test, large samples values will almost be same. So that's why in many of the softwares, there is only t-test, because t-test can be used for small samples, and it can also be used for large samples, because for large sample, it approaches to that test. So that's why in many of the softwares, only t-test is given. Hopefully you understand this point. Yes, please. Is this clear? Hello?
Yes,
Yeah.
sir.
Okay.
Yes, sir.
Yes.
Now, where to use t-test? Where to use t-test? T-test can be used for testing of single population mean. Like I want to test height, that mean height mu is equal to mean mu is equal to 157 centimeter, or weight, like mu is equal to 60 kg, or IQ, that mu is equal to 100. Then difference of two population means, I want to compare two different populations, Assam population, West Bengal population. So hypothesis will be mu1 is equal to mu2, or mu1 minus mu2 is equal to 0, one and the same thing. Then I'll again use t-test. Paired data. Sometimes we have, just like I have given you example that patients are coming to the OPD, doctor examine their blood pressure and they are suffering from low BP. Then doctor give them medicine and call these patients say after 4 months. So one reading is before giving the treatment. Another will be after 4 months after giving the treatment, right? So they are present in pairs. It's the same set of patients before and after situation. One value is before, another is after. Okay. And if you have such type of problem that you want to see what is the improvement, what was the values before, and if there is any improvement after, that means the medicine is effective if there is improvement. But if all the differences are 0, that means the medicine is not effective at all. So for that purpose, again, t-test is used, paired data. Yesterday, we have seen that for testing of correlation was also based on t-test. Right? Correlation is also using t-test. Then f-test is used for equality of two population variance. For example, if I want to test, let's say, I want to compare height of Assam people and West Bengal people, mu1 is equal to mu2. But somebody may want to compare variances also. sigma 1 square equal to sigma 2 square. For that purpose, we use F statistics. Then one-way ANOVA is used because t-test can compare only up to two groups. Only two groups are compared with the help of t-test. Suppose I want to compare 3 groups, 4 groups, 5 groups, then I have to go for one-way ANOVA. Then there is two-way ANOVA. Then there is multi-way ANOVA. So all this we will discuss. And here I'll take up example of t-test and then give you practical example before we move on to the break. So here is a one sample and independent t-test and pair t-test. So we'll try to finish these 3 before 4:30. And later on, I'll come up to one-way ANOVA, two-way ANOVA, repeated ANOVA, all these things, right? Okay. Can we say that the mean weight of a certain population is different from 60? That's a claim. So under H0, we always put equal to. So I'll write the H0, mu is equal to 60 kg. Alternative will be mu not equal to 60 kg. Now there is only one parameter. Which parameter? Weight. Only one parameter. So that's why this is called one sample t-test. This is called one sample t-test because you have to take only a sample of people concerning with weight. That's all. Because of weight is the only thing. Then second is, does the mean weight in two regions differ significantly? Already given you an example of West Bengal and Assam. Now, then you have to take two different samples, one from West Bengal, another from Assam. And these two are independent samples. And if there is no difference in their heights or weights, then hypothesis will be that mu1 minus mu2 is equal to 0, or you can say mu1 is equal to mu2, that there is no difference in their mean weights or mean height. Against the alternative, that they differ. Why it is called independent t-test? Because you have to take two independent samples, one from West Bengal, another from Assam. Another, whether the medicine is effective in controlling blood pressure or not. So let's say X is before taking the medicine, before giving the medicine, Y values are after taking the medicine. And then you take these differences, Y minus Xi. If all the differences are 0, if all the differences are 0, what do you think? The medicine is effective? Yes, please. If there is no change in before and after, do you think the medicine is effective or ineffective?
Ineffective.
Ineffective. The medicine is ineffective. Same thing, not only to the medical terminology, you can apply to yourself. For example, today I have given you what is null hypothesis, what is alternative hypothesis, what is parameter, what is how to estimate it. And I have given you definition of type 1 error, type 2 error, p-value. Let's say right in the beginning, when we started the class at 2:30, I give you a questionnaire in which all the questions are related to type 1, type 2 error, null hypothesis, all these things. And after 7 o'clock, because we have a class up, I again give you the same pro forma. So one is before giving the training, another is after giving the training. But if the differences in the scores are almost 0, what do you think? The training is effective or not?
Ineffective.
It is not effective then if the differences are 0. So it's not necessary that you have to apply to the medical field. Wherever before and after situation is there, you can go for t-test, right? So here we test the hypothesis mu is equal to something. Here we test mu1 is equal to mu2. Here we test mu d. Mu d stands for differences in before and after. That's why I write mu d is equal to 0. So if I accept the hypothesis, medicine is not effective. I should reject this hypothesis so that medicine becomes effective. So hopefully these t-tests are clear. And here is the test statistics which I will be using. So I will be using this t-test for one sample t-test, single population mean. For example, suppose I want to test this. Mu is equal to 60 kg. Now, from this population, I take a sample of 25 people. Okay, I take a sample of 25 people. That is my n. So now in this is your n. N is 25. Now, if I am having 25 observations relating to weight, so I can compute the mean weight, add 25, divide by 25, so X bar will be known to you. I can also compute the variance of the sample. That is the formula to compute variance. You will not have to compute. R will give you this value. So variance can be computed, mean can be computed. What is this mu naught then? Mu naught is the value which you are presuming under H0. So under H0, what you are presuming? That mu is equal to mu naught. Mu naught is your 60. So this will be 60. So everything will be known to you. Everything will be known to you. X bar is known. Under H0, mu is known. Sx square you can compute. N is also known. So you can compute the value of this test statistics T. Yes or no? Yes, please.
Yes.
Right?
Yes, sir.
And this will always be having T distribution with n minus 1 degrees of freedom. Now, what are these degrees of freedom? You can write down the definition, please. Write down the definition for degrees of freedom. If you are carrying a pen or pencil, degrees of freedom are nothing but the number of independent observations which form the statistic. Degrees of freedom are nothing but the number of independent observations which form the statistic, form FORM, which form the statistic, minus MINUS, minus the number of restrictions, minus the number of restrictions. Now, how many degrees of freedom you have which form the statistics? X bar is based on how many observations? N number of observations. But what is the restriction here? Restriction is here that we are subtracting mean from every observation. We are subtracting mean from every observation. This is a mean. This is any observation. So we are taking these differences. That is one restriction. That's why the degrees of freedom are not n. It is generally one less than the number of observations. So observations are n. Degree of freedom will be n minus 1 because there is one restriction in computing variance. And another way to look at whatever is the division factor. Here we are dividing by n minus 1. That will be your degree of freedom. How the S square is computed, right? That will determine the degree of freedom. So this is how one sample problem we can solve, and it will give you a p-value. You just have to compare p with alpha. Then independent t-test. What is independent t-test? Let's take this example. Used to compare difference between the two types of groups, like West Bengal and Assam. Let's take this example. Suppose we put people on diets. People on diets, two types of diets. Let's say I put 10 people on pizza diet. They like pizza. So breakfast pizza, lunch pizza, dinner pizza. And another group of people are given normal diet, whatever we eat, rice or pulses or whatever, right? Now, for 1 week, one group is given pizza diet. Another group is given normal diet. What is the problem? Problem is after 1 week, I want to see which group is having more weight gain. So I'll assume this hypothesis that weight gain due to pizza diet is same as weight gain due to normal diet. Or you can write mu1 is equal to mu2. Mu1 is a parameter for pizza. Mu2 is a parameter for normal. So if there is no difference in weight gain, it will be equal. Against that, this is not equal. Now there are two groups. So that's why this becomes independent t-test or two sample t-test, right? And for this will be the test statistics will be computed. I'll take up a sample from pizza diet, compute its mean, compute its variance. Take up a sample from normal people, normal diet people, take up their mean weight and also their variance, then compute the pooled variance. And then this will be test statistics. Everything is known. N1 is known, N2 is known. S square I can compute from here. And degree of freedom will be, for first sample, it will be, you are taking a sample of size N1 from pizza, N2 from normal. So for degree of freedom, for the first one will be N1 minus 1. For the second will be N2 minus 1. Since it's a two sample, so add the two. N1 minus 1 plus N2 minus 2. So degree of freedom will be N1 plus N2 minus 2. So this is called independent t-test. And the last is, before we move on to practical example, paired t-test. Paired t-test, as I mentioned, before and after situation. So before giving the treatment is Y, after giving the treatment is X. So differences are pre and post. Pre scores and post scores, right? And we are testing this hypothesis that mu D is equal to 0. That the difference is equal to 0 in the population. And the test statistics will be this. So I'll compute all di values. The first d1 value will be y1 minus x1. Second will be d2, y2 minus x2. y1 and x1, they are known to you. y1 is before giving the treatment, x is after giving the treatment. So compute all the differences, d1, d2, dn. And now once the values of d1, d2, dn are available, you can compute d bar. You can also compute their SD and then use this formula. SD of the differences, mean of the differences, divided by under root of n is your sample size. Degree of freedom will be again n minus 1. Right? So this is called pair t-test. So hopefully you are clear where to use one sample t-test, where to use two sample t-test, where to use paired t-test. So this completes your theory part. Now I'll move on to application part with R. Right up to 4:30, we will be able to do all the test. Any question if you have, most welcome to ask, please. If you have any question in mind, you can ask me before I move on to practical example. But theory was more important. Yes, please. Any question?
Yes, sir.
Any question you want to ask, or should I move on to practical example?
Yes, sir. Am I audible?
Yes, I can listen to you.
So actually, I want to know. Actually, it is a very confusing. Like every time I saw that the error in statistics, when we use in statistics type 1 error and type 2 error, which one is more serious, sir? Like somehow some says it's type 1 error and some says it's type 2 error.
Very good question. Let me answer this question. Okay. See, what is type 1 error? Reject H0 when H0 is true. Something is of good quality and you are rejecting that, right? So that's no doubt it's a serious error. But what is type 2 error? Accept H0 when H0 is false. Something is of bad quality, you are accepting. That's why consumer's risk. This is called consumer's risk. Let me tell you, type 2 error is much more serious than type 1 error. Now you will ask me why. If you want to see that there is a mathematical proof also, and if you want to see the proof, there is a book. That book is called Modern Mathematical Statistics, and it is written by Dudevix and Mishra. Both of them are Americans. Dudevix and Mishra's book, you can go through the mathematical proof that why type 2 error is more serious than type 1 error. Of course, sometimes because type 1 error is fixed in advance. Type 1 error is fixed in advance. You cannot fix type 2 error. So type 1 error is in your control right in the beginning, but not type 2 error. That's why type 2 error is more serious than type 1 error. Hopefully I able to make you understand. Yes, please. Yeah. Anybody else? Any other question? So should I move on to the practical example?
Sir.
Yes.
Sir, actually, I got a question. Sir,
Yeah,
when
Mishra
we
साहब, पूछिए.
जी सर. सर, जब हम बोलते हैं कि लेवल ऑफ सिग्निफिकेंस मतलब टाइप 1 एरर का 5% होना चाहिए. सर, तो इसका मतलब ये है कि हम लोग
टाइप 1 एरर का 5% नहीं होना चाहिए. नहीं, आप मेरी बात सुनिए. टाइप 1 एरर का 5% नहीं होगा कुछ भी. 5% is not, it's not a level of significance. Basically size of type 1 error is, probability of type 1 error is what is called size of type 1 error. Now what is level of significance is how much you can afford in your experiment. Let's say कोई एक्सपेरिमेंट बहुत कॉस्टली है. मैं आपको हिंदी में जवाब दे रहा हूं कि बहुत एक्सपेरिमेंट कॉस्टली है और उसमें से अगर एक सैंपल जो है वो 60,000 का एक सैंपल आ रहा है, तो आप 100 में से अगर आपके 5 सैंपल खराब हो गए तो आपका कितने का नुकसान हुआ? 3 लाख रुपीस का. कैन यू अफोर्ड दैट? कैन यू अफोर्ड दैट और नॉट? नहीं कर सकते ना. सो देयर यू नीड द लेवल टू बी वेरी वेरी स्मॉल, कि रिजेक्शन मेरी कम से कम हो. So that's why we fix the level right in the beginning of the study, depending upon how sensitive the experiment is. So level of significance is always fixed in advance. But generally, if your experiment is very sensitive, you can take this 1%. Even you sometimes cannot afford even 1%. I'm talking of a general manufacturing process, जहां पे हम 5% लेके चलते हैं. This is what I'm saying.
Yes, sir.
Yeah. Any other question?
Thank you, sir.
Any other question? Okay. So I'm moving on to practical examples now of one sample t-test, independent t-test, and then pair t-test, one by one. Can you see my desktop now? Yes, please. Hello.
Yes, sir.
We can
So
see
let
the
me open
file.
R and let me open R. Okay. Can you see my screen? Is it visible?
Yes.
Okay. All right. So this part we have already covered yesterday, like correlation regression, correlation testing. This was all. Then multiple regression also. Let's go for hypothesis and testing. Can you see this line? Hypothesis and testing problem.
Yes.
Yeah. Okay. Suppose this is the data, and this data is concerning with weight. Suppose this data is concerning with weight. So I am having weight of few people, 62, 73, 84, 73, 63, something like this. And somebody wants to test that. Can I say that the mean weight of this population is 65 kg? Mean weight of this population is 65 kg. Okay, that's a problem. Now, what is the hypothesis? So here I have written hypothesis that mu is equal to 65 kg. Alternative will be that mu not equal to, mu stands for mu not equal to 65 kg. So that is the hypothesis. This is null hypothesis. This is alternative hypothesis. Okay. Now for that, because sample size is small here, it is just 10, 12 observation. You can check the length, how many people are involved. Length of X. So if I give this and run from here, sorry, let's just pick up one value. So this is your X. So I have taken 11 people only. So it's a small sample. So to check this claim, I have to apply t-test. One sample t-test, because it is concerning only with one parameter, that is weight. So the command is t.test, whatever is your value X, and then mu. Mu, what do you want to test? You may test mu is equal to 0. You may test mu is equal to 70. So put the value of mu is equal to 65. That is the value under H0 you want to test. Is that okay? Yes, please. So t.test, the data and the whatever you want to test under H0. So apply this, you will get this answer. So the test statistics, I have shown you X bar minus mu divided by S by under root n. That has been computed. And this value is coming out to be 2.2643. How many observations were there? Yes, please. How many observations were there? 11. So degree of freedom, can you see the degree of freedom? How many? 10. And what is the p-value here? Yes, please. P-value is how much?
0.04.
0.04. Is it less
Less
than
than.
0.05 or more than?
Less than.
Less than. So if p-value is less than 0.05, will you accept H0 or will you reject H0?
Reject H0.
Reject H0. Because whenever p-value is small, you are rejecting H0. How small it should be? Less than 0.05. There is no need to see any statistical table. So you will reject H0. What was H0? Under H0, mu was 65. So certainly, mu is not 65. Mu is not 65. It is different from 65. Yes or no? Right?
Yes. Yes.
Now, somebody can say, if it is not 65, then whether it is greater than 65, you can check the mean value. Let me check the mean value, mean of X, and compute the mean of X. So mean is coming out to be 73. So now alternatively, what you can say that yes, whatever is the claim, that is not true. The mean weight is not 65 kg. If somebody asks you whether it is greater or less, so you can look at the mean. So can you tell me whether it is greater or it is less? Yes, please. It's greater than
Yeah.
65. So your answer is
Yeah.
yes, this is greater than 65, right? Okay, here is another example of a simple t-test. Let me show you the data. This is relating to BMI. There was a population and weight of the people were increasing. Weight of the people were increasing, right? It should be another example. Let me put this one. Okay. Now, idea struck to somebody's mind that let's check their BMI. BMI is an indicator of body mass index is an indicator of obesity, overweight, underweight problem. So roughly, if BMI is less than 18.5, then the person is underweight. If it lies between, so rather than 18.5, let me take roughly as 20. So if it is less than 20, person is underweight. If it is between 20 to 25, so let's say BMI level is between 20 to 25, then it is a normal person. If it is between 25 to 30, overweight problem. If it is beyond 30, then it is an obesity problem. So idea struck to mind, why not to check their BMI level? So this person has taken some random sample and computed their BMI. BMI, there is a method to compute. You take the weight in kg, divide by the height in meter square, you will get BMI levels, right? So let me go through I will read this from my directory. My directory is AKD, if you remember. So now you are into get working directory. Check whether you are into AKD. Yes, I am into AKD, because all the files will be available only when you are into your directory. So I have already gone through this yesterday also. Now I will pick up one file. That file is here. So there is no need to give the path now. There is one file with the name of BMI. I'll look at this file. Run this. So you are already into the data. Let's look at this file. So you can see this with the help of this command here only. View data, but V is capital here. Remember. So view data. So this is your BMI. Can you see the BMI levels? Hello? These are all BMIs. Let's say BMI of first person is 23, of the second person is 25. One sample only, 21, 37. Right? So this is BMI. So I'm just closing the data and back to the program again. Now you have seen the data. Now what we want to test, whether this data or the people, they are having the normal BMI level or they are moving towards obesity. That is the entire crux of the problem. Whether they are having normal BMI level or they are moving towards obesity, right? Now, what is the normal BMI level? Between 20 to 25. If you are having a pen or pencil, please write down. If your BMI is less than 20, indication is underweight. Between 20 to 25, normal. 25 to 30, overweight. Greater than 30, obesity. Okay. All right. Now, let's again the same test, but now here it is written X. So it will check that X data, but it should be actually data. And I need to attach this data so that BMI is independently available. Attach data. This. So view data we have seen. I'll attach the data so that individual values of BMI available, right? And value of not data, it should be BMI then. Let me see what was this is BMI, small BMI. If this would have been capital BMI, you should have written capital BMI. So that's why I need to look at. So it is BMI. Mu is equal to this. So I apply this test and here is the one sample t test. So your N is equal to, there were 25 observations. N was 25. And now you can see T, this is a T value that has been computed and degrees of freedom is one less, that is 24. And this is a P value. It is 3.887 into 10 raised to power minus 5. That means it is 0.000, then 0, 3887. So very, very small p-value. Very, very small p-value. If it is very, very small p-value, hypothesis will be accepted or rejected? Yes, please.
Rejected it.
Rejected. So what was H naught? Mu is equal to 24. 24 lies. Why I have taken 24? Because it belongs to the normal period, normal BMI, 20 to 25. But it says that these, suppose I would have accepted this. If you would accept this, that means these people are having normal BMI level. There is no problem at all. Right? But now I have rejected this. Now, next question comes whether people are having overweight problem, underweight problem, or obesity. Go for the mean. Go for the mean. Mean BMI. Check this value. If you compute the mean, it is coming out to be 31. And 31 is beyond 30. And beyond 30 means people are moving towards obesity problem. Yes or no? Hello?
Yes.
People are moving
Yes, sir.
towards obesity problem. So you have to ask the people, please don't eat pizza, burger, noodles. Your weight is increasing, right? Restrict yourself, all these things. Okay. So this completes your one sample t-test. Any question in one sample t-test, please? Or is it clear? Is it clear? Hello?
Clear.
Clear. Okay. Now let's move on to two sample problem. In two sample, there will be one sample concerning with X, another sample concerning with Y. They may not be equal length, not necessary to be equal length. There may be, for example, I want to compare mean weights of West Bengal and Assam. And you take a sample of size 60 from Assam people. You take a sample of size 100 from West Bengal people. Doesn't matter, right? They may be unequal. They may be unequal. I can add some more observations. Suppose 134, 156, 170, and so on. And you can go for the length. Length of, what is the length of X? And here also length of Y. Length of Y. Check this. So if you click here, all X values are here. So there are 11 values in X. And this is Y values. There are 14 values in Y. They may not be equal, not necessary. Now, what is the problem? So we want to test, here it is written, we want to test mu1 is equal to mu2. If you remember the hypothesis, this is my hypothesis, H naught. At H naught, you want to test mu1 is equal to mu2 because it's a two sample problem. One sample is X, another is Y. Is it clear? Yes, please. Hello?
Yes, sir.
Yeah. So we want to test mu1 is equal to mu2. Right. Now, whatever we are testing, we are basically testing mu1 is equal to mu2. But these two are different populations. One is population values under X, another is population values under, sample values under X, another is sample values under Y. They are coming from some population. X is coming from some population, Y is coming from some another population. Okay. Now I'm testing about mean. But think of that variance of these population may be equal or may not be equal. Yes or no? I mean, sigma 1 square may be equal to sigma 2 square. Sigma 1 square is concerning with X. Sigma 2 square is concerning with Y. These two may be equal or these two may be unequal. Yes or no? Hello?
Yes.
Right? Now, so first of all, if there are two types of t-test actually to be computed. One type of t-test, if the variances are equal, then I will use the t-test with equal variance. But if variances are unequal, then I will use the t-test with unequal variance. You follow my point? Anybody?
Yes, sir. Yes.
So first of all, here I am basically testing variances. So for testing variance dot test xy. I'm testing this variance. So if you test the variance, so this is the answer. F test to compare two variances and look at the p-value. So what is the p-value here? Yes, please. What is the p-value here? Yes, please. बताइए भाई कितना p-value है? ये कितना है?
4014.
0.4014. What I'm testing basically, initially, I'm not testing t here. I'm testing variance. So it says you are testing basically sigma 1 square equal to sigma 2 square. And p-value is more than 0.05. Yes or no?
Yes.
So if p-value is more than 0.05, that means H0 will be accepted. H0 will be accepted. What was H0? H0 was that sigma 1 square equal to sigma 2 square. That these variances are equal. Variances are equal. So that means if I'm computing t-test, I will be computing the t-test with y assuming that there is a equal variance. You follow my point?
Yes.
So that's why this t-test I have to compute by giving that I want to compute t-test between x and y, but by assuming that variance dot equal to is equal to true, because I have tested that. Hello?
Yes.
Right? So I will make use of this variance dot equal to is equal to true. Run this, and this is the p-value. So it says t-value is this. Degrees of freedom are 23. Why 23? Because length of this was 11 plus 14. 25 minus 20 minus 2. N1 plus N2 minus 2. So 25 minus 2 is how much? Yes, please. 25 minus 2. Hello?
23.
23. So you can see the degrees of freedom 23. And we are assuming that variance, if I'm not giving this variance is equal to true, suppose I remove this. The next I have done this. If variances are not equal, suppose this hypothesis at the initial stage would have been rejected. Then I would have used this one. Not equal variances. You follow my point or not? If variances are equal, I have to put variance dot equal to equals true. If they are not equal, then I can go ahead with this, which is by default. So by default, it assumes that variances are not equal. But if variances are equal, then you must use variance dot equal to true. Right? So this is your p-value, 0.0626. Yes, please. Actually, we are testing the hypothesis mu1 is equal to mu2. This is what we are testing. Now, this is your t-value. This is your p-value. Is the p-value less than 0.05 or more than? Hello? P-value is 0.06. Is it more than 0.05 or less than?
More than.
More than. If it is more than 0.05, H0 will be accepted. And what was H0? Mu1 is equal to mu2. That means there is hardly any difference between these parameters of x and y. They are almost equal. They are almost equal. Right? So this is what the result is. Let's take another example and then we will go for another example. So this is another example. I have to read the data from t-test. I'll show you the file here in view data. See, I'll run this. And if you see the view data says, see, experiment is like this. Please try to understand. Should I give you the break and then we'll continue? Will that be okay? Hello? Hello? Should I give you the break? If you want a break, then we can maybe assemble at 5 o'clock today, and then I will continue from here. Will that be okay?
Yes, sir. Yes, sir.
Yeah, because it's becoming too tiring now for the last. I'll go through the t-test, then pair t-test, and then we'll move on to one-way, two-way NOVA. That will be finished by today, maybe by 6:45 or maybe before that. Okay. So I'm just